jeszcze minutka. Tak, nawet przedstawię. Prawie. Okay, I think we can start. Welcome. Today our seminar will be given by Karolina Dziadura, a PhD student from Poznan University. The title involves asteroids, which are not discussed here very often, so we're glad you're here. And it's based on Gaia mission, and it's very similar to the title of Karolina's PhD thesis, which was already submitted. So we can give her feedback at the end, I think. Floor is yours.
Thank you very much. I will do a speed run of my most important results that I obtained during this PhD studies. The title is Determination of Physical and Dynamical Properties of Asteroids Observed by the Gaia mission. And my supervisors are Przemysław Barczak and Dagmara Oszkiewicz from Poznan Astronomical Observatory, of course. So I will discuss the asteroids, the orbit determination, the Yarkovsky effect, which is the main topic of my studies, and my research goals and results, publications, and of course, summary and future prospects. So when it comes to asteroids, maybe they're not that, for some people, they are not that interesting as galaxies and stars, but for me, they are really interesting because they are just so close to us, and we can actually touch them and see them, and even touch some dust or some rocks from them. That's because there were a lot of asteroids which were visited by spacecrafts, and of course, we have a lot of meteor craters on Earth, and the biggest, there are some bigger one because theoretically one of the asteroids hit Earth 66 million years ago and killed dinosaurs and created a Gulf of Mexico potentially. But my main interests are the close asteroids, especially near-Earth objects, especially in my personal case, potentially hazardous objects, because they are dangerous and we should observe them and mitigate the impact with them. There are some groups of asteroids divided because of their orbit. You can see near-Earth asteroids, which include also potentially hazardous objects, mine belt, which contains the most of asteroids in our solar system. We see Hilda and Trojans, and far away we have distant objects, which are Trans-Neptunian and Kuiper belt. And here you see the same plot as before, but on the other angle. So you see that the mine belt is actually like a torus. And here is the representation of it. It's just here that the orange dot here is Jupiter. So you see how far away are the asteroids which are not in the mine belt. So it's a lot of them, and they are really, really far away. I really like this graphic. But what I mostly do, I use asteroid astrometry from different sources. The main source of asteroid astrometry is, of course, Minor Planet Center, which contains all of the astrometry collected from all over the years. So it's a screenshot from last week, so it's already updated. They have more objects and more observations, but it's almost up to date. All time, they have over 437 million of observations, of astrometric observations of asteroids, and we have discovered over 1,300,000 of asteroids, which is quite a big number. When I started my studies, it was less than 500,000. So with automatic observations, we discover more and more objects. And there are near-Earth asteroids, which are quite important. There's only 34,006 of them. But also we have a different type of astrometric measurements, so-called astrometric because it's not astrometry. I want to say about radar data, which I also used in my research. So I download radar data from JPL because some of it it's available at Minor Planet Center, but not all of it. So I downloaded from JPL to be sure that they are all of them. But they have some constraints. The asteroid has to be quite large and it has to be a near-Earth object because if the object is too far away, we are not able to reach it with radar. And radar observations are really important because they the parameter is linked to distance and radial velocity. Therefore, it's really important because one measurement from radar data is way more accurate than a few hundred observation from ground-based observation like the optical telescopes. Moreover, I used also asteroid occultations for my research. So we can from asteroid occultation we can have a lot of results, not only astrometry, but also we can derive it to determine the size of the object. On the left, you can see the ephemeris of one of the occultations events, and so it basically works like solar eclipses, but we don't eclipse solar, but we eclipse the really distant star, which we assume it's a point source because it's that far away. And asteroid comparing to the star is way more closer. Therefore, the shadow path on the Earth is the same size of the asteroid. And then translating it, I have one more slide later with the methodology how I do it. We can translate it to the size of the asteroids, which is really important. But what is also important in Minor Planet Center, we have a lot of astrometric measurements from occultations. They are also way more precise than typical astrometry, but we don't have a lot of them. But I use them as well for my orbit computation if they were available in MPC. And last but not least, my data source, because I combine all of them, is Gaia. So Gaia was designed for stellar observations, but it also contains a lot of asteroid astrometry. But since it was designed for stellar observations, there are some constraints that are really hard when we have to deal with asteroid astrometry. But first of all, here on the left, you see the Gaia scanning law, because Gaia is trying to cover the whole sky as dense as it could be covered. And Gaia has two telescopes which observe at the same moment, and it spins, and because of the spin, the objects observed just go through the focal plane of this CCD, which is so far the biggest CCD that we launch to space. So when it comes to stars, it just goes, a star goes to the sky mapper. And because it's a really huge CCD, if it has to give us the whole CCD to Earth, it would be a lot of gigabytes of data. Therefore, they just do a small square around the object. And this when the star is going to this way, this square is just following the object. But when we have a asteroid, which is a moving object, especially when we have closer asteroids, which are faster moving objects, because of the distance, they can escape the square. That's first of all. And second of all, they just move on the square, and Gaia is only scanning in this along scan direction. And across scan directions comes only from SkyMapper. And therefore, asteroid astrometry from Gaia is highly correlated. Here is the representation. So we have a piece of CCD camera that contains asteroid astrometry. And you see that Gaia provides the along and a cross scan, and then recalculates it through using the scanning angle to see to actually get the right ascension and declination. But as I said, the along scan is way more accurate, and the cross scan, which is coming from just the sky mapper, is just way more uncertain. And that's why I did a lot of tests to use the data properly. And here's a plot that shows post-feed residuals of asteroids astrometry. Here's a declination and right ascension. The gray dots are representing all of the astrometry from MPC, and just from MPC. And the colorful dots represents asteroid observations from Gaia. Each line and each color represents different transits. And by transit, I mean like just going the asteroid through the whole focal plane of CCD camera. And when we just have it on declination and right ascension, it looks like this. But when we change the direction for the scanning angle, we obtain the across and along scan. And you see that the residuals goes like this. And you see that the along scan residuals are just way smaller than the across scan. Here on the right, it's just zoomed in comparing to the left one. And that is why I have to if we want to use Gaia data of asteroids, we have to use the whole covariance matrix of the data, which I mean the systematic and random errors, including its correlations. Here's just a summary of Gaia data. In Gaia data release 1, there were no asteroids. In Gaia data release 2, there were over 1,400 asteroids and only astrometric positions. And this Gaia data release 2 I used in my first part of the studies. And then when Gaia DR3 was released, I extend my studies for more objects, because here we have over 158 thousand asteroids, which is a lot. And not that long time ago, Gaia Focus product release was released, and it has almost the same objects as Gaia DR3, but with double observations of 4 asteroids. But I didn't have the time to include the computations here in the presentation. So for this presentation, I have only up to here. Okay, so when it comes to orbit determination, which was the main topic of my research. So it started really long time ago from Aristarchus of Samos, who was actually the first who proposed the heliocentric theory, but it didn't go well. But then the Copernicus did it one more time, as we know. Then we have Kepler, who formulated the 3 laws of planetary motion using Tycho's Brahe observations of Mars. Then we have Newton with its Principia, then Edmund Halley, who established the orbit of comets, Halley, then Euler, who formalized the Newton's method. Then we have Limbert and Gauss, whose methods are used today, to date, and Laplace. And now, since we have way more complicated telescopes to observe, and our observations are just so accurate, we have to use more complicated technologies to compute orbits. And that's why right now I was using Orbit software, who was using the Waitnik least square problem. So here's just a function that we want to minimize. M is the number of observations, W is weight, and here are the residuals. I don't want to go into details because I have a lot of results to discuss later. So my main topic was the Yarkovsky effect. So here's a representation of the Yarkovsky effect. When we have, so basically this effect is a change of the orbit of asteroids based on the solar radiation of the solar energy. So here's the solar radiation, here's the asteroid. And if the asteroid has a retrograde rotation, the Yarkovsky drift will decrease the orbit. And if we have a prograde rotation, the Yarkovsky drift will increase the orbit. But we have all, besides the diurnal, we have also a seasonal component of the Yarkovsky effect. Seasonal will always lead to the increase of the semi-major axis. For asteroids with diameter over 100 meters, the diurnal effect is dominating. And the effect is negligible. Sorry, I don't know how to spell this word. Negligible for bodies with diameter over 40 kilometers. And most importantly, it depends on physical properties and orbital properties of asteroids. That's why if we want to determine it really well, we have to also know the physical properties of asteroids, not only a good orbit. But even though it was proposed over 100 years ago by Yarkovsky and then popularized by OPIC 50 years later, the first time it was discovered for not for the asteroid but for the satellite, Lagos satellite. Then in 2003, the first discovery was made thanks to Arecibo radar observations of asteroid Golevka by Stephen Chesley. So far, the best known Yarkovsky effect is for asteroid Bennu, and that's because of the OSIRIS-REx space mission. However, the asteroid Bennu also have some non-gravitational acceleration, which comes also from its activity. So for computations like up to date, for some comparison, we use Apophis, which is the second best known Yarkovsky effect, and we know it that well thanks to not any space missions, but thanks to its close approach in 2021 and its stellar occultation observations. So as I said, stellar occultations can give us a lot of data. The Yarkovsky effect is really important for us to determine the collision probability. Of course, it's basically a seventh parameter of the orbit. So the more parameters we have, the better the function will be. So it just increase the accuracy of the orbit. Of course, the dynamical evolution of individual asteroids as well as for asteroid families and populations. And in the end, if we have a good determination of other parameters, we can also determine the density of asteroids, which is the least known parameter of asteroids because we just don't have data. When we talk about the Yarkovsky, I just have to mention Yorp effect, which is something that works at the similar way, maybe I can say that, but it doesn't change the orbit. The Yorp effect changed the rotational period of the asteroids. So my scientific goals and results, my main goals of my PhD and my studies was to determine sizes of for selected Gaia mass asteroids. Then after doing that, I realized that we really need a good orbit to determine stellar occultations, which I will discuss a little bit later. And I got interested in orbits also using occultation data. And I use Gaia data because they were available up back then already, and they use it to determine the Yarkovsky effect. And I was struggling in the beginning of with using Gaia data along with MPC and radar data because they are really tricky to use. And then when I had a tool to do it, I do it one more time using Gaia DR3 and using a new OrbFit software for orbit computation and new weighting scheme, which I will discuss also here in this presentation. But starting with asteroids, how do we compute sizes of asteroids using the stellar occultations? So first of all, we define the coordinate system, which is which takes right ascension and inclination of the star. And as I said, those observations are way more accurate comparing to asteroids, typical astrometry, because we don't do asteroid astrometry. We just take the astrometry of stars, which are typically well known. Therefore, the precision is just way better because we take it depends on the precision of this specific star, which was occulted. And then we determine the points, which are basically on this focal plane. We put points of the observer, the moment of the star, when the star disappeared, and the moment when the star appeared again. And we calculated for the and we put it on the focal plane as those two points. And also in our computations, we were using the uncertainties of those observations, which was a new approach comparing to the older softwares. And as you see, sometimes you have green lines which are outside body, and they are basically observers who didn't observe the occultation. And this happens because we don't have accurate orbits of asteroids. If we had more accurate orbit, we would create a more accurate prediction, and we would have observers in points which they would be able actually to observe the event. And in the end, if we have those points, we then use just basic chi-squared methods to put the model and to fit the model the best we can, and we just scale the model, and based on that, we have the size of the asteroids. Moreover, our software we usually used models because I cooperate with Przemysław Barczak, who is just responsible for the models based on the what's it called? Light change curves. Krzywa zmian blasku? Light curves, just light curves. But our software is also could also take just a sphere for that computations, and the results will be less accurate, but still good. Here's just a few examples from the paper that we published. We compute the size of 9 objects, and here is just a few examples. For example, for Juno, we have a few occultations events for different dates, and as you see, it depends of how many observers we have. Sometimes the coverage is pretty good. Sometimes we just have 2 lines, but 2 lines are enough for the size determination. If there's only 1, then it's a little bit tricky. And then later, as I said, I get into orbits because of my previous studies, and I started using OrbFit, which was created by Andrea Milani, and it was also collaborations with a lot of people, as you see here. The newest version is 5.0.7. It's been written in Fortran. It has a lot of components that you can use for different reasons, but in my case, it was computing orbits. There are a few weighting schemes for observations, because when we compute orbits, we are dealing with observations which are spread in times, sometimes even 100 years. And when you think about the observatory from 100 years ago, you can just think of the techniques that they were using, and you know that they were not as accurate as we have right now. Therefore, we have to properly weight observations, so we don't use all of them the same. So we use different weighting schemes. And I was using this one because the newer version was for the asteroids with the short arc of observations. So here's my first results. In the first paper, I was using this version of OrbFit that I mentioned here. So 5.0.7, which is available online still. And I was using this weighting model because it was the only one available back then. And I used Gaia DR2 because also DR3 was not available yet. And I used some of the near-Earth objects, and I was trying to look for the Yarkovsky effect for them. And I compute the Yarkovsky effect was just the 7th parameter, as I mentioned before. And after that, first of all, I compared my results with previous research. In most of them, you see my result fits pretty well, but it has a smaller uncertainty, which is a great result because that's something that we are looking for, actually, because we want to confirm the previous studies. But for some, like here, we see that this point is just the opposite, has the opposite sign. But I double checked it and then I computed later with more data, and I like right now I know that this is a good result. They just didn't. They used a different technique. They used a different observational arc, which is the most important. They didn't use Gaia data, so like this all influenced the result. Later, what I also did, I was trying to confirm my results because, of course, I can compare some of them, but I have a few new of asteroids that they were not published yet. But some of the objects could be it could be a systematic error. So there are different techniques to validate our results. But here I used two to see how it looks like. So what I did, I compute the expected value of the Yarkovsky effect based on physical properties of the asteroid, if they were available. For most of them, the size was available because of the NEOWISE mission, which provides a lot of sizes of asteroids. But other parameters were usually not available, like, for example, density, which I just assumed based on its other properties. And I used the Lavinia paper, and I used his equation, and also used a Greenberg approach, which turns out it was less constrained. And later, when I compute the expected value, here's the A over dt, which is basically a change of the A in time, which is A is the semi-major axis, of course. And this is the same as I will later say A2. They are both non-gravitational transverse acceleration, just in a little bit different units, but I don't want to go into details. I will say Yarkovsky effect, the expected value of Yarkovsky effect. And what I did, I use my results and divided by the expected value. And this was S value here. And if S value was less than 2, I assume the value was accepted. It was bigger, I assume it could be something wrong with data. It could be some systematic errors. And we just prefer to publish something that we are 100% sure of, and not publish something that in a year will be just say that it was wrong. So we have a few accepted objects. Here on the vertical line is the signal to noise ratio. So another constraint, if my result was had a signal to noise ratio over 3, I also assume this as accepted. So here you have accepted objects. And I use only 42 asteroids for this computation. But later, I had more experience in using Gaia data, and I visited Minor Planet Center, and I got the access for the new version of Orbit, which included using Gaia data in way easier. It was just way easier compared to the older version, which I had to adjust the format, and it was really, really complicated. When I just remember how I did it here, it was just so much work, and here using Gaia data was just way easier. And also I confirm my results in a previous way, so I just had to use more asteroids, more data, and just do automatic computations. But I not only have a new orbit computation, or OrbFit for orbit computation, I also got the access for the new weighting scheme, which I was responsible for testing. So as I said, there are a few weighting schemes available for OrbFit to use. They were really simple, and Federica Spotto, who I collaborated with, she designed a new, really complicated weighting scheme. And in this weighting scheme, we take into account the magnitude of class of the asteroid, year that the observatory was made, and the catalog that was used for the astrometry, and the way of observations, if it was a CCD camera or was it a spacecraft, and of course the observatory. So from all of the millions of observations that they were all downloaded and divided into those classes based on those 5 parameters, and based on that they were divided into groups, and based on that we were trying to see how they act depending on those 5 parameters, and based on that we created a really huge weighting scheme for the orbit computations. As you see here on the left, we have RMS of right ascension and declination. Using Gaia is also, of course, the best for asteroid astrometry, because Gaia is the best. And here I just plotted the same, but just constrained it a little bit more, because it's just out of points. And you can see the older catalogs that are here that were used for astrometry. So as I said, I was responsible for testing of this weighting scheme. I did it for a few objects. I don't show all of them here, but basically what I did, it was really simple. I compute orbits using the older weighting scheme and the new weighting scheme, and I was observing the results, especially the residuals, which shows us how the weighting scheme works. So the blue dots are the ones when I use this new weighting scheme. Red ones are when I use the older weighting scheme. And in all of my results, the confidence ellipsoid, the blue one was inside the red one. It happened to all of my cases. And so basically we know that our huge weighting scheme, which actually takes a little bit longer to use than the previous one, because it's just a little bit more computations, it's just better. And here's just Amun and Apophis. Those are just 2 examples for that. But here in Apophis, I observed those 2 strange features. So I double checked what was that. And those are just systematic errors of 2 telescopes. This whole group of observations comes from this observatory, and this as well. They both happened in 2021 during its close approach, and Apophis has just a really huge observing campaign, and this is something we have to deal with when we compute orbits. But we don't want to remove those observations because we don't know if they are good. Maybe all of them they are wrong, but we have to weight them properly and use all of them, because we just don't want to remove observations, which of course we do remove observations during the fit, but it happens automatically based on chi-squared and threshold method. And during each iteration, some of the observation can be recovered. And in the end, we just remove a few of them. So if we have like thousands of observations, we remove a few, then I think it's fine. What is more, I compared my results of using this new weighting scheme for orbit computation, and I compared my results using OrbFit. Here's again, as I said, A2 is a non-gravitational transverse acceleration. So basically, the Yarkovsky effect computed using OrbFit, the new version of OrbFit, and new weighting scheme compared to JPL results. And in JPL, they have a different method for the orbit computation. S values as before, A computed in this work divided by A2 expected. So basically, most of them fit pretty well with a few exceptions, which are probably the reason. The reason for that is could be a few things. Of course, they are using a different method. Second of all, they made use some observations that they had that was not published. Sometimes it happens. And lastly, I know the people who are doing that, and I know that they are doing a lot of manual intervention into observations, and sometimes they just do some manually, which I don't know if it's good way. We do everything automatically, and we use the same thresholds for each observation and for each asteroid, but they do some things automatically, manually. But as I said, it fits pretty well, but I observed that my results have usually smaller uncertainties, which was quite good. So in the end, I used MPC data. I added radar data, of course, if they were available, so only for near-Earth objects. I added Gaia DR3 data, and I used a new weighting scheme, of course, with the new orb fit. And I took all of the near-Earth asteroids in Gaia DR3, which were 446 of them, and I compute the Yarkovsky effect using Gaia DR3 and without Gaia DR3 to observe what's the difference. So again, I will mention it one more time. S value represents the A2 value computed in this work divided by the expected value based on physical properties. Here I used the Lavinia approach because it was more constrained, and I used so basically it was comparing the result to the Apophis results because we use it as a basic asteroid. And here's this horizontal line represents the signal to noise ratio 3. So again, if S was smaller than 2 and signal to noise ratio was bigger than 3, we said that the value was accepted. We had a few marginal cases, which are the ones which have a signal to noise ratio between 2.5 and 3. And when we added Gaia DR3 data, maybe it's not that easy to observe, but basically the whole plot just moved a little bit closer to the accepted objects, and we had 9 more accepted asteroids, which is a lot for the Yarkovsky effect because they were new objects, and so far we have only technically there are some publications, and technically we have over 300, around 300 asteroids with the Yarkovsky effect, but that accurate as here only less than 100. So 9 more is a really good approach. But this was not the only way we checked our results, because we wanted to be sure that it's not any systematic error of the results. So I compute the orbit of each of the asteroid using different data sets, using different observational arc. So I started from the newest observations, and I just used the latest 5 years of observations, and I compute the Yarkovsky effect. I added 5 more, computed the Yarkovsky effect, and again. Even here for Phaeton, I think it was even for every 3 years. So as you see, and when I only use a 5 year of observations, the Yarkovsky effect is here, and the uncertainty is quite large. To compute the Yarkovsky effect for that big of asteroid, we usually need at least 10 years of observations. Therefore, this is just not enough. Then here you see that when I'm adding a little bit more observation, that the result is just floating here, and here is my result with a really small uncertainty. So as we see, when the result is acting like this with adding more and more data, that means that it's a good result. Sometimes for some cases, we saw that the result is only based on pre-recovered observations or based on some old observations, like here for Eros. So Phaeton is a really typical good result. Is a really good representation for a good result. And here is Eros, which is a bad result. And that's why we decided to remove it from our accepted group. So you see, it looks like it's starting from a really big value, then it goes down into a really small value. Here's just a zoomed in area of the results. And from the positive results, then it after 1950, it jumps into the negative value and it goes here. So my result was based on observations which were older than 100 years old, which is something that it's something that we shouldn't rely on. If you want these results to be accepted, it should be also visible somewhere earlier, maybe with a bigger uncertainty, but it was not. Second of all, Eros spin axis was suggesting that this value should be positive. And we know Eros pretty well because Eros is one of the asteroids that was visited by spacecraft. Therefore, we decided to remove it from our list, even though similar to this result was published in other papers, but we think that it's wrong. It's just wrong. Also, Eros is quite large. It's a 30 kilometers asteroid, so the Yarkovsky effect should be really, really small for that big of the asteroid. What is more, I computed, when I realized that I have that good results, I decided to do more with it than previously. So I plotted the d over dt over the diameter to see how it looks like. Here's the function that we determine based on that, only for accepted and marginal near-Earth asteroids. This is something that we also observe in other papers, in one other paper, and we wanted to compare our results to them, and it looks pretty similar, but this is something that to be expected, that the Yarkovsky effect should be smaller for bigger asteroids and should be bigger for smaller asteroids. And here, this point is really far away from others, but this is Phaeton, again, as here, this asteroid. But this asteroid is really interesting because it has a cometary activity, because it has some ice on it, and its orbit is really elongated. Therefore, sometimes it's really close to the sun. And because of that reason, it fell into the accepted objects, because sometimes it's just so close to the sun. And this plot just takes into account diameter. It doesn't take the semi-major axis or eccentricity. That's why it looks like this. If we add more detailed equation here using eccentricity, it just goes here. And on the left, as before, I compared my results to other papers if they were available. And as you may see, the uncertainty in my case is way smaller, and this is because of using Gaia DR3 data. Just basically using a small amount of Gaia precise astrometry, because sometimes it was 1,000 or 10. Okay, just for one asteroid it was 10,000. For example, 5,000 observations from MPC and 150 observations from Gaia DR3, and it was enough to have a better orbit. So basically adding Gaia and using all of them, but properly using the all covariance matrix of Gaia gives us a really nice result of better orbits. Here I just plotted those two asteroids that were far away from the feet, comparing to the literature, but I double checked them and I just know that my results is correct, including my really small uncertainty. Comparing to the quite large. And lastly, as I said in the beginning, from the Yarkovsky effect, we can determine the density of asteroids. So that's what we did. We decided to use our double-checked results that of those almost 60 asteroids that we were really sure that they were good results, that we double-checked using those two approaches before, and we decided to compute the the density of the asteroids. To do it, we reverse the equation of the expected value, and we use other parameters of the asteroids. If they were available, if they were not, we created the probability density distribution of the parameters, and we just try to do it as accurate as we could, and we dependingly on the parameters, we just added the uncertainty. And all of it's just a part of the paper. The objects is the list is a little bit longer, and that would be all for that paper. I would like to summing up with the 3 papers that I was actually discussing here, that are a part of my PhD. So first of all, the physical parameters of selected Gaia mass asteroids. This was the part that I started with. I'm not the first author, of course. This was the part that I started with. I compute the sizes of asteroids using occultation data, and because of that, I got interested and started going deeper into orbits, which goes here to investigating the most promising Yarkovsky candidates using Gaia DR2 astrometry. And here I started using OrbFit and Gaia data together, and it was really complicated. I did a lot of tests that are described in the paper, but I didn't have the time to show it here. But I just wanted to be sure that I'm using Gaia data properly. And I was using a few different approaches. For example, I was using a nominal point of observations and all of Gaia observations to see how the result varies. And here I learned how to use Gaia data, and here I publish the Yarkovsky effect and bulk density for near-Earth asteroids from Gaia DR3. I didn't mention it here, also because of lack of time, but I also compute here orbits of over 50,000 in inner main belt asteroids, because so far we have the Yarkovsky effect only for asteroids in the near-Earth objects. But no other objects. Therefore, using Gaia DR3, I was trying to compute it for inner main belts. It didn't succeed. I had some results with signal to noise over 3, but they were not something that I could rely on. So in the end, this is just a summary that I basically mentioned already, summing up the papers. But I think that like the most important summary is here, that using this Gaia data is really great. It's really complicated to use it properly, but when I finally started using it as they should be used, I got a really nice results, and I discovered some new Yarkovsky effect for a few new objects, which I was very happy about. And in the end, we determined the density, which I collaborated with Benoit Carré from France. And the future prospects, it's something that I already started to do, but it's not included in my PhD yet because it's just a new research. So first of all, repeat the computation using Gaia focus product release. I already did that. I submitted a paper, but the revision is just so hard. I didn't manage to reply to it yet. Then search for the Yarkovsky for non-NEA, as I said. In DR3, we were not able to do it. Maybe in focus product list, we will be able to do it. Using it to close approaches to Earth. The history already showed us, especially with Apophis case, that including Yarkovsky effect into computations just basically cancel the Apophis from risk list. Therefore, we know that if we want to talk about any impact probability distribution, we should include the Yarkovsky effect. Another ongoing project is photocenter barycenter offset, which is shown here. So right now we are in the era where we have such accurate data that we can observe other effects in it. And we have, if the data is so accurate, we should start including other effects like photocenter barycenter offset, which was not able, we were not able to see it in ground-based data, but in Gaia data we can actually see it. And this photocenter barycenter offset is just basically a difference between the photocenter of the asteroid and the actual center of the mass of the asteroid. And if we have not that accurate positions, then it doesn't matter. But if we have really accurate observations, this small difference is actually visible in data and in our residuals of orbital fit. Therefore, this is something to be included, but this also this effect also depends on asteroid sizes and asteroid distances. So we have to use all of the parameters, and we can better determine it when we have a model of the asteroids. So again, we have to use it all to study the objects. We cannot just pick one direction and just compute orbits without looking into other properties of the asteroids. In the end, of course, Vera Rubin telescope is coming. It used to be called LSST. And it's coming, and it's they say that they will discover a lot of asteroids, and the plan is to discover 5 million asteroids. I don't know, we will see, but it's going to start observing really soon. I mean, it depends what, like, I don't know, next 2 years, next year. And sizes, masses, and density determination using Gaia data, also another plan of Gaia collaboration. That will be all. Thank you very much for listening to the presentation.
Okay, thank you for the talk. We now have time for questions. Please don't be shy.
I'm interested in the topic that you about the occultation observation.
Yep.
What are the sources of the observations? Who is actually doing that? And are there any amateur astronomers involved and local astronomers? And how?
Okay, I will repeat the question maybe because they probably online.
But I mean, could you tell more about activity around this?
More about?
Is there any coordination effort between those?
Is there any what? Sorry. Cooperation.
Is anyone coordinating that?
Okay, so most of the observations of the occultation observations comes from.
Sorry, the question.
Sorry.
The question was about the occultation observations and how they done, and by who.
So most of them comes from amateur observatories, observers, because they are really easy to do. If we talk about brighter stars, you just need a small telescope and fast CCD camera, which is not that expensive as it used to be. Right now, we can just use a few thousand and it's fine. And there's a lot of people who just love to observe and be a part of the research. And I actually was at one conference, which was called ESOC, which is organized by amateur astronomers who are committing to occultations. And it was really amazing because the people there were just, even though they were not professional astronomers, they were just so knowledgeable, and their talks were really interesting. So basically, most of the data comes from amateur astronomers, but if we want to observe something with a fainter star, we need a bigger telescope. So there are some observatories which observe with a bigger telescopes which are not amateur astronomers. And when it comes to collaborations, and there is a lot of collaborations, especially it was when there was a close approach to Apophis. Basically just the community talk about where they are going to observe. Moreover, there are some crazy people in the US who basically takes a container full of telescopes, goes somewhere, and they are trying to catch usually trans-Neptunian objects, which are the least known objects because they are just so far away, they are so faint, and it's hard to observe them because The orbit is uncertain because it's so far away. Therefore, we have a data with a small arc, and based on small arc, we have to determine the orbit, which is harder than when we have a full arc of observations. And if the orbit is way more uncertain, then sometimes they just have, I don't know, 20 telescopes in like a few kilometers, and they don't observe anything. But there are some, so they are basically, there are some professional campaigns and some amateur campaigns.
So when it comes to this type of observations, if you could go to the slide with the Juno that was shown a few times. The shape.
This one?
Yes. So what is RMSD and what are the units?
So this is RMSD represents the how good is the fit. So it's computed based on this it represents like the for each point, because again, sorry, from the beginning here this is line, but actually it's a 1 point in the beginning and the second point in the end, and we are trying to fit those points. So RMSD represents how it's just a basic representation of how good those 2 points fit to the shape of the asteroids that we have here.
Other questions, comments?
Łukasz
has some. Oh yeah, people from the internet. Łukasz, go ahead.
Okay, hello, I hope you can hear me. Very nice presentation. Thank you for this. I have many questions, but I'll select one. So actually looking at this slide you're showing here, so these objects, they are not spherical, right? And you use this data, but this is a projection, right? And then the radar data, maybe radar data is more, it has some time factor in it. So it can tell you a little bit more about the 3D shape. But in principle, you just use one parameter for the shape determination, which is the diameter. So I guess you must be assuming somewhere under the hood that these objects are spherical. And how does it influence your results? Because the reality is different, right?
Sorry, but you're asking why I'm using those shapes that are not spherical?
What's the effect of, you're assuming spherical objects, but they are not. How does that impact your results?
I mean, here we were using models which were created by the light curves.
You mean shape models?
Shape models that were created from light curves. And we were stopping them at the time of observation and taking the edges as a projection of the objects, and then using the occultation to fit properly the shape. But as I said, I don't know if I'm answering your question, but as I said, we can also use a sphere here, and the result will be a little bit less certain. But technically, it's still a good result. It's still way more better than computing this from the photometric, like the normal photometric observation, because the photometric observation also depends on the albedo, which we usually don't know it. So even if we don't have shape and we use it, if we don't have model, if we use a spherical shape for this fit, it's still a good result.
Because it must have some influence on the Yarkovsky effect, right? If the shape is not spherical, and if they have these fancy valleys and so on, it must have some impact, right? And you probably do see it in your data, I'm sure.
Unfortunately not.
No? Okay.
Yeah, when it comes to shape, the Yorp effect is affected more by shape of the asteroids. But when it comes to Yarkovsky effect, it's more affected by the diameter.
Okay. I see.
Not...
Thank you.
Thank you.
we have time for last short question. I don't see anything on the internet. Nothing here. Okay, thank you very much.
Thank you.